Hello students, good morning. And in today's class, we are going to talk about the electrophilic substitution reactions of benzene. So the following topic might be helpful in understanding the electrophilic substitution reactions of benzene in the beginner level. C6H6, the benzene aromatic compound, why it is undergoing electrophilic substitution reaction. The reason is very simple. Benzene is an aromatic compound in which there are 3 pi bonds are available. Each pi bond is going to have 2 electrons, so totally 6 electrons are there. These 6 electrons are delocalized electrons. Delocalized electron means they are common for all the 6 carbon atoms present in the benzene. Thus, we can understand the benzene is electron rich. So, any electron deficient species, namely the electrophile, can be readily substituted. Okay, because it is rich in electrons. What type of electrons are available? Delocalized, so that we can say it's an electron rich center and quite often attacked by the electrophile. So in this category, the first would be the electrophilic substitution of benzene, in which the first one, nitration of benzene. What's the meaning of nitration? Nitration means substitution of nitro group, NO2 plus group in the benzene. So this electrophile is to be substituted. How to generate that electrophile? For that purpose, we should use a mixer called as nitrating mixer. What is the composition of nitrating mixer? It is constituting the concentrated nitric acid and concentrated sulfuric acid. The concentrated nitric acid can be given as follows. We can write it as HO, N double bond O and single bond O. When it is in contact with sulfuric acid, H plus and HSO4 minus. In the nitric acid, oxygen is containing 2 lone pair. When one of the lone pair is given to this hydrogen, this is called as protonation, adding of proton, addition of proton. So that we will be getting the protonated form HO, H, and N double bond O, single bond O, this is carrying plus, and HSO4 minus. So after getting the protonated form of nitric acid, consecutively the water is getting eliminated from this. So on the removal of water, we can have a species like this, N double bond O, single bond O. The group of atom carrying positive charge, and it can behave like electrophile. Now we are going to substitute this electrophile in the benzene ring. Okay. How this can be substituted in the benzene? First of all, I will write the reaction followed by the mechanism. So in the case of benzene, and you know the structural formula, it is the structure for benzene in which one of the hydrogen is taken outside conveniently, and when it is treated with the electrophile like this, it will be getting this pi electron. So due to the attack of electrophile by using these two mixer, we will be getting the substituted benzene, namely the nitrobenzene. The compound formed is called as nitrobenzene with the loss of H2. Its mechanism is explained as follows. So we will try to write the mechanism for this particular reaction. The benzene ring, in which conveniently I will be taking one of the hydrogen outside. Now the NO2 plus what is generated with the help of nitrating mixer is going to approach this benzene ring, and it is getting this pi electron pair. So once the nitro group is substituted in that particular position, we can have an intermediate HNNO2. So due to the loss of electron, this carbon can carry positive charge. And the other resonance structure, in order to make it neutral, this pi electron is moving towards this side. So we can have one other intermediate as follows. This is the intermediate mode, HNO2. Now this position is positively charged. To make it neutral, it is moving. So other resonating structure we can expect. This is the other structure which is possible. Yes, we can have a double bond here, and the H is there, and NO2. Now this position is carrying plus. So to make it neutral, the hydrogen is removed in the form of H plus. So this step, the last step, is deprotonation. At the end of the deprotonation, we can have our desirable compound, namely the nitrobenzene. So in this pathway, the reaction can be completed and we will be getting the nitrobenzene. And this is the expression for nitration of benzene. So the nitration takes place in the following mechanism. In any order you can take. So in the beginner level, you may have some doubts. And why don't we take like this? The nitrobenzene, even in this position, the hydrogen is taken outside, and the NO2 plus is attacking me. This pi electron can also be used because all the pi electrons are equivalent. Okay. And the other topic after the nitration, we are going to talk about the next one. Sulfonation. Sulfonation means substitution of SO3 group, otherwise introduction of SO3H in the benzene ring. So this is behaving like an electrophile. And how to generate this electrophile? For that purpose, we can take concentrated H2SO4, in particular the fuming nitric acid. What is called fuming? In a container, when you have a concentrated sulfuric acid, some of the vapors are getting released, SO3. You know that the combination of H2O and SO3 is nothing but H2SO4. So this is the gas which can be avoided. And highly concentrated sulfuric acid from which the sulfur trioxide can be obtained. Now this sulfur trioxide can behave like an electrophile in the following substitution. Okay. And even when you take a diluted form of acid, the HO, SO3H, in which due to the catalytic cleavage, the sulfur takes up the pair of electron, so that you will be getting something. Oxygen is taking up the pair of electrons so that we can have OH minus and SO3H plus. So this is also an electrophile. There are two ways. When you take fuming sulfuric acid, this is the electrophile SO3. When you take concentrated sulfuric acid, this must be the electrophile. Anyway, finally, we are going to substitute SO3H in the benzene ring as follows. Directly, I will write a mechanism. You just take a benzene ring. As usually, one of the hydrogen is taken outside. Now, SO3, it is getting electron from this benzene ring. The SO3 which comes from fuming sulfuric acid, H2SO4, highly concentrated. So what would be the intermediate? And this is the intermediate, H. And after receiving the electron from this, it might be carrying minus SO3 minus temporarily, because we were taken a neutral form of sulfur trioxide. On getting electron from the ring, now it becomes electron rich, SO3 minus. And this is the position carrying plus. The next intermediate resonating structure can be written as follows. When the pi electrons are shifted towards this side, you can have electron deficiency in one other position. This is the position carrying plus. Consecutively, in the next stage, we are going to get one other resonating structure. When the pair of electron is moving towards this side, you will be getting this particular substance, the HSO3 minus, it carries plus. So finally, to make it neutral, the hydrogen is giving electron and the electron pair is utilized by the benzene ring. So at the end, the hydrogen which is leaving from that, and that might be combining with this SO3 minus to form SO3H. SO3 minus, this is SO3 minus, which is protonated at the end. So final product, it can be called as benzene sulfonic acid. The sulfonic acid which differs from the carboxylic acid. Carboxylic acids are having COOH. Sulfonic acid is having this functional group SO3H. Benzene is bonded with that, and hence it is called as benzene sulfonic acid. And other reaction under the same electrophilic substitution reaction of benzene, it would be chlorination. How to chlorinate benzene? The chlorination can be done as follows. Just take a benzene molecule and it must be treated with Cl2 in presence of a catalyst, namely FeCl3 ferric chloride, and we will be getting the chloro substituted compound. Its name is chlorobenzene with a loss of HCl. So this is the compound word called as chlorobenzene. And what's the mechanism behind that? Chlorine, we know it's a covalent molecule. It's a sad pair of electron. When it is in contact with ferric chloride, the ferric chloride can behave like a halogen carrier that takes up Cl in the form of Cl minus. Both the electron pairs are taken by the Cl. Heterotic cleavage takes place. Due to that, Cl is carrying plus. And when you attach this Cl to FeCl3, it becomes FeCl4 minus. So we know that Cl plus can behave like electrophile. So for the generation of electrophile, it's very important to have this substance, namely ferric chloride, that behaves like a halogen carrier. So in the next stage, in the consecutive step, the reaction mechanism as usually can be explained as follows. I'm writing that mechanism. Take a benzene ring in which in one position one of the hydrogen is taken outside. When the Cl plus is approaching, the pair of electron is available for the Cl plus, so that in the as usual manner you can have an intermediate. This is the intermediate mode, and in order to make it neutral, the pi electrons are in movement, so that leads to the formation of another resonating structure. This is the possible resonating structure, HCl. It is carrying plus. When the pair of electron is moving towards this side, we will be having other resonating structure. The intermediates are formed as follows. Yes, we will be having this intermediate, H and Cl. At the end, we are having FeCl3 Cl minus. That Cl minus may contribute electron to this hydrogen plus. So the hydrogen is removed as a H plus. So on the substitution of chlorine to this benzene, we will be having Cl attachment plus HCl. The compound what is finally formed is called chloro-substituted compound. It is said to be the chlorobenzene. Nothing wrong when you write like this. The alternate double bonds can be written as follows. So in one of the way you can able to mention the chlorobenzene is thus formed. So far you have seen the nitration, sulfonation, followed by chlorination. For the chlorination, the reagent required is FeCl3. Likewise, the same benzene can be brominated. Suppose if you want to carry out the bromination reaction, you must go with ferric bromide, because in the bromine there is a covalent bond, and the ferric bromide will take up the Br in the form of Br minus, so that the electrophile can be generated on the introduction of the electrophile in the molecule of benzene. Can have a compound. It's a compound made by the name bromobenzene. So the only difference for the introduction of bromo is to take ferric bromide, and for introduction of chlorine you should have ferric chloride. So that's all about the halogenation as well as chlorination, bromination. Now we are passing on to the other simple matter called as Friedel-Crafts reaction. Friedel-Crafts alkylation reaction as well as acylation. What is called alkylation? Alkylation is nothing but substitution of alkyl group, or is to be introduced in the form of electrophile. And the explanation can be given as follows. Take a benzene, and to that benzene we will be taking CH3Cl. You know this compound is called as methyl chloride, called as chloromethane, and it must be treated with anhydrous aluminum chloride, AlCl3. That would be the reagent in the Friedel-Crafts reaction. What's the importance of anhydrous aluminum chloride? And you can understand that anhydrous aluminum chloride is a halogen carrier. Why this is behaving like a halogen carrier? CH3Cl. There is a covalent bond, AlCl3. You know that it is electron deficient. and it can behave like a Lewis acid, and hence it takes up Cl in the form of Cl minus. So due to that, you can have CH3 plus and AlCl4 minus. Thus, merged CH3 plus can behave like electrophile. Okay, so the electrophile can be substituted in the benzene ring. On the introduction of electrophile in the benzene, you will be getting this structure CH3 plus HCl. The compound's name is toluene, also called as methyl benzene, methyl substituted benzene. And its mechanism is also in the similar manner. I'll write the mechanism of the same reaction. How this can be substituted, the methyl group. This is the idea. You just write down one benzene structure with alternate double bonds. Take a hydrogen. When the electrophile is approaching this benzene, it will be getting the pi electron from the ring, so that the substitution can be made, and it would be the substituted form. Yes, I'm rewriting that. The benzene, just take a benzene ring. In which the hydrogen is taken outside, the CH3 plus that gets the pair of electron from the ring structure, so that it is the intermediate uptime. The hydrogen as well as CH3, both of them are there, and this position is carrying plus. To make it neutral, this positive charge should be made neutral. For that purpose, we should shift an electron from this particular position. This pi electron is moving towards this side, so that we can have another structure, the HCH3. Now this is carrying plus. When the pair of electron is shifted towards this side, yes, you can have this particular phosphate HCH3. This carries plus. And AlCl4 minus we have got already. That Cl minus will give electron to this hydrogen. So this pair of electron is utilized by the ring. At the end, this is the methyl substituted benzene, namely methyl benzene. The methyl benzene is also called as toluene. It is a way to get toluene molecule. I think you are all following. It's very, very simple. It's the simplest task to follow this matter. All are possible with the help of same mechanism, same reaction pathway, in which so many number of intermediates are made while the introduction of electrophiles. Just have a consolidation. These are all the electrophiles so far substituted in the benzene ring, and electrophiles are listed here. This is the nitro group NO2 plus, and the sulfur trioxide sulfonation we were seeing. The halogenation we were seeing. Halogenation, there are two types, chlorination and bromination we were seeing. Now we are discussing about the introduction of alkyl group like CH3 plus with the help of Friedel-Crafts alkylation reaction. In a similar manner, we are having one more Friedel-Crafts reaction. The other Friedel-Crafts reaction is Friedel-Crafts acylation reaction. It is also called as acetylation reaction. Fiddlecraft's acylation come acetylation reaction. This acetylation reaction can be explained as follows. Yes, we can have Fiddlecraft's acetylation reaction. It is the reaction. You just take CH3, C double bond O, OH. We are all familiar about it. It is acetic acid. Its derivative is an acid chloride, CH3COCl. This acid chloride is called as acetyl chloride. The acetyl chloride from which you can able to get CH3CO plus. Now this can behave like an electrophile. So introduction of this group CH3CO plus is commonly called as acylation or acetylation reaction. So how to generate this electrophile and how the reaction mechanism, that can be given as follows. I am writing the equation. Take a benzene ring and that should be treated with CH3C double bond O Cl in presence of anhydrous aluminum chloride AlCl3. And we know that it's an electron deficient substance. So CH3C double bond O Cl acetyl chloride on action with AlCl3, it is leaving with electron. So AlCl3 will capture this halogen to form AlCl4 minus, and the other product would be CH3C double bond O plus. This is nothing but acetyl group, also called as acyl, and the introduction of this is called as acylation reaction. So on the introduction of this group in the benzene, it's a product expected. We will be having COCH3. First gets CO. It's a ketone. One is methyl, other one is phenyl. So you can call it as methyl phenyl ketone. Methyl phenyl ketone is also called as acetophenone. How to get this acetophenone through the reaction mechanism? Reaction mechanism is very well known for you because so many examples we have discussed so far. In the same old mechanism, we are going to complete this reaction also. Consider the benzene. Even this hydrogen can be taken outside. CH3C double bond O plus. This pi electron can be given to this carbon. Any carbon you can take because all are equivalent. Okay, and this will be the intermediate of time. The bond breaks up and the hydrogen is already there. Now COCH3 is introduced. It is carrying plus. To make it neutral, this pair of electron is shifted towards this side. The other intermediate is formed. This is the intermediate what we are expecting, HCOCH3, and it carries plus. To make it neutral, this electron pair is moving towards this side so that we will be having this formula. The H is there, COCH3, and this is carrying plus. To make it neutral, finally Cl minus, which comes from that AlCl4 minus, will abstract this hydrogen so that the electron pair is moving towards this side. We can have a neutral compound, the final product. This is the final product merged, COCH3 plus HCl. It's a ketone. Its formula can also be given as follows: C6H5. Instead of writing the ring, C double bond O CH3. In one side, we are finding the methyl group in opposite phenyl, and hence the compound's name is, this is the compound merged, COCH3, C6H5, C double bond O CH3. This is called as methyl phenyl ketone. Methyl phenyl ketone, also called as acetophenone. Both the things are same. So apart from the acetylation or acylation, one more reaction can also be given for Fiddlecraft. That would be benzoylation reaction. What is it? Fiddlecraft's benzoylation reaction. Benzoylation means we will be taking the benzoyl chloride, C6H5C double bond O Cl, an acid chloride which comes from the benzoic acid. When it is in contact with AlCl3, the same way by which you can have AlCl4 minus, and electrophile will be C6H5 C double bond O plus. Benzoyl group can be obtained. Okay, benzoyl group. If you introduce this benzoyl group in the benzene ring, yes, take a benzene ring that must be treated with C6H5 COCl and anhydrous aluminum chloride. On introducing this group, final product can be understood as follows. It's a final product merged with the loss of HCl. And we can have the other formula for this C6H5 C double bond O C6H5. It is said to be the diphenyl ketone. Diphenyl ketone is also called as benzophenone. So these are all the various examples of electrophilic substitution reactions of benzene in the introductory level. And in the forthcoming levels, we can have so many derivatives of benzene. The benzene derivatives, they can also undergo this reaction. So an example of benzene derivative, which means you just take a benzene, and to that benzene, we can introduce a functional group like OH. So it becomes hydroxybenzene. It is called phenol. It can undergo electrophilic substitution reaction. And other benzene derivative, this is the benzene derivative, methyl benzene, called as toluene. It can undergo this reaction. And other benzene derivative, we can have OCH3, called as methoxybenzene. It will undergo the same electrophilic substitution reaction. And we will be having the other one, CHO, as a functional group. It's an aldehyde. It is called as benzaldehyde. It can undergo the electrophilic substitution reaction. Other one, COOH. It is called as benzoic acid. That will also undergo the electrophilic substitution reaction. And even we can have NH2. It is nothing but the aminobenzene, also called as aniline. So these are the most common substituted benzenes. Benzene derivatives, they can undergo the electrophilic substitution reactions. Those nitration reactions we can discuss in the forthcoming sessions. Okay, thank you. With this, we can conclude this session.